Sengolrajan, sir.
Yes, sir.
Sir, are you ready, sir?
Okay, sir. I am ready, sir.
Okay, sir. We will start with the inaugural session, sir. I will call with my vice principal, sir. Sir, vice principal, sir. Okay, sir.
Yes, sir. Yes, sir. Yes, sir.
Sir, you are also ready, sir. Shall we start
yes,
with
sir.
the
Yes, sir.
session,
Yes,
sir?
Yes, sir.
Okay,
Yes,
sir. Okay, sir. Okay, sir.
Good evening to one and all present here. Intelligence is enrolled, but wisdom is learned. SRM PRP College welcomes you all participants for the Day 2 National Level Webinar, National Level Workshop on Dimensions of Control Systems. Now I'd like Mr. Hubert Tony Raj to deliver the welcome address. Thank you.
To one and all present here in this virtual gathering. First, I would like to welcome our chief guest, Dr.T.Sengolrajan, sir, Associate Professor, Kongunadu College of Engineering, for his presence to deliver his knowledge on applications of controllers in power electronic circuits. We welcome you, sir.
Welcome, sir.
Next, I would like to welcome. Thank you, sir. Next, I would like to welcome our beloved Vice Principal, Dr. B. Ramasubramanian, sir, to be in our part to this workshop. We welcome you, sir.
Thank you, sir.
Next, I would like to welcome our beloved HOD, Dr. P. Langovan, sir, to make his workshop into great heights. We welcome you, sir. I would like to welcome my faculty friends and my real-day heroes, our participants, for this wonderful session. Once again, I welcome you all for this virtual gathering. Thank you.
Thank you, sir. Now I invite our Vice Principal, Dr. Subramanian, sir, to felicitate the gathering.
Thank you, sir. Hello, sir. Am I audible, sir?
Yes, sir. You're audible. Sir.
Okay, sir. Thank you, sir. So, very good evening to one and all gathered here. On behalf of SRM management, principal, I welcome you all for this 2 days national level workshop on dimensions of control system. I wholeheartedly welcome our chief guest, Dr. Sengolrajan, sir. So thank you for accepting the invitation, sir. Thank you, sir.
Thank you.
So actually, we know very well that the world is moving towards Industry 4.0. But for that, for achieving that one, so this online educational system helped us to achieve, to move towards this Industry 4.0. Because if you consider offline classes, there may be a possibility for us to teach classical notes using blackboards and all. But if you see this online classes, that is online educational tools and online educational system, it helped a lot to learn about the practical applications of all the field, particularly for the TRPEC students and the TRPEC faculty members. It will be very useful to learn about the different types of controller applications, everything. So, so actually there will be a saying that if suppose a person is hungry, if you catch a fish and if you give him, it will be useful for only 1 day. But instead, if we teach him or her the art of catching the fish, it will be very useful for his entire life. So like that, this online tools, these online workshops will definitely help us to learn many things in our life. So I hope there is so I don't want to take much of the time. Once again, I welcome all the faculty members from other institution, all the students from other institution, and my dear student and my dear faculty members for this 2-day national level workshop. So before that, I also want to thank the organizers, the HOD of TRPEC department, Ilogo sir, and the coordinators, Professor Tony sir, Kripa ma'am and Kritika ma'am. So thank you so much for taking a lot of efforts, ma'am. So thank you so much. So thank you, sir.
Thank you, respected sir. Now it's time to introduce our chief guest. Dr.T.Sengolrajan sir did his BE in Electrical and Electronics Engineering in Annamalai University by the year of 2003. He continued his masters on Power Electronics and Drives in Aruna Engineering College and earned his degree by the year of 2010. He did his doctoral degree under the specialization of Instrumentation Engineering from Annamalai University by the year 2018. He is currently working as Assistant Professor in Kongunadu College of Engineering and Technology under the Department of TRINARY. He has a good experience for about 15 years. His research interest is on multi-level inverter, Z-source inverter, renewable energy, and IoT-based smart energy distribution. He has published about 17 SCI journals, and he took part in 24 international and 8 national conferences. To add with, he also published for this virtual meet. Sir, now you may deliver your speech.
Yes, sir. Good evening to one and all present for the forum. First of all, I thank the management of SRM TRP, Principal Sir, Vice Principal Sir for inaugurating the second day of the national level workshop. Then I thank the department of the HOD Tribly of SRM TRP, Dr. Elavan Sir, who is my junior colleague and well-wisher for the past research carried out for the 15 years so long in the teaching fraternity. Then I thank Professor Tony Raj for inviting me, and he has been coordinating for the past along 15 to 20 days, and he has been used to get discuss the topics and what are the things I am going to carry out, and for arranging all these brochures. And also I thank the organizing committee and over. I welcome all the participants around. There are 1 or 2 participants, including my 2 devices, in the forum for the discussion, to hear the discussion on the dimensions of control systems. I welcome all of you. Now I will share the presentations. First, the title, it is a dimensions of control systems. First of all, before going on to this theme of the dimensions of control system, a system is nothing but a number of components that is being connected together. Then if a number of components is being connected together without applying the control, the system will perform according to its wish. But we as a human being wants to control the system and to perform the actions what we decide, so that only we are applying a control to whatever the systems what we decide to get the objective. So in that aspect, this topic is being chosen, I think so. That is dimensions of control systems. What are the ways by which we can apply a control system to the domains of electrical engineering, such that we can be able to obtain the desired objective or the desired output functions. So in that regarding, I have been chosen, that is, I can have a control over the power electronic circuits for medium level applications as well as for high level applications. So based on that sense, I have given this topic as applications of controllers in power electronic circuits. That is, in the power electronic circuits, I have been chosen, there are the most current trending, that is the MLI, multi-level inverter. I have been chosen the power electronic circuits, that is the multi-level inverter MLI, and as well as the advance or the enhancement of the multi-level inverter is Z-source inverter. That is ZSI. Then beyond the Z-source inverter, there are many derivatives that is been came into existence. Then what is the advantages of MLI compared to the conventional inverters? In the conventional inverter, if you have been choosing the level of 3 or 5 or 7, 9, 11 or etc. in the order up to the nth level, it can perform only its chosen level only. But if you want to get the output voltages with less harmonic distortion as per the standards, and the output functions to meet our medium voltage applications as well as high voltage applications, we are being going for this multi-level inverters. Then going on to the Z source inverters is in the Z source inverter, there is a special concept called the shoot through concept. This shoot through concept will boost the output voltage beyond the input voltage in the order of 30 to 35%, which will reduce the cost of the component. So this is the plant I have been taken in the power electronics domain, that is the multi-level inverter as well as the Z source inverter. This is the plant I have been chosen. To this plant, I am going to apply a control techniques. Whatever the possibility of control techniques, we can apply. In the similar manner, I have been taken the power electronics domain. In the similar way, you can take any domain. For example, if you want to control the smart grid, you can go for IoT firmware. Then if you want to control the smart distribution systems, you can go for machine learning, deep learning, artificial intelligence, and all the advanced techniques, neural networks, starting from GA up to particle swarm optimization, any technique. Then if you can go for all as well as renewable energy source, either solar, wind, you can go. Then with that, you can go for the MPPT algorithm, or there is any techniques, any advanced techniques, and you can have the control such that you can meet the desired objective. So in this manner, we can have any dimensions. There are n number of dimensions. You can go in what way you want. You want to control the system, and the system has to meet out your desired objective, that is the output, without much more distortions. If you are not applying a control to that system, it will be just the oscillatory in nature. So that only to whatever the system we are going to model, either in simulation or in real time, we have been applying a control. That is been in the colloquial language, we will say that is the techniques. Suppose if somebody has been achieved with some task in a greater manner, means what we will say, we will go and ask what techniques you have been followed, what strategy you have been followed, such that you have been obtained this in a higher manner that I cannot be able to do. So that is mean we will say that is a strategy or and technique. So in that similar manner, we are going to apply a control strategy or and control technique to these MLI circuits, as well as the Z source inverter circuits, and we are going to analyze the performance parameters of percentage total harmonic distortion, percentage distortion factor, as well as the VRMS voltage, peak to peak VRMS voltage. We are going to analyze these three parameters with the carrier signal which we have been chosen to the same plant, and we will be taking the level, a common level to the same plant. The different carriers we will be using. Then with the different carriers, we will be using different references, but the control strategy is same, remains same, and we are going to analyze how these control techniques or the strategy will work to analyze the performance of the MLI circuits as well as the Z source circuits to achieve less total harmonic distortion, better VRMS voltage, minimum distortion factor in the output waveform. This is my objective towards the lecture. That is, I have been taken, this is the dimension of control system regarding taking the power electronic circuits and applying the control strategy or the control techniques and moving it to achieve the better performance. This is one way I am moving. This is my dimension. You can choose in that similar manner. You can go in n number of dimensions to the electrical engineering domain, and you can have your objective to be meet out. Then the things you are going to, at the end of the presentation, you are going to gain a knowledge on the what are the various control techniques that is mean in the current trending in the research of multi-level inverter, and how we are going to implement those control techniques in the simulation, that is MATLAB Simulink, how we are going to model the system, and for the same model using Simulink, we will be analyzing which carrier is better to the same plant with the same techniques, and to that best technique and best reference, we will be developing the model using FPGA implementations, SWATRON 3E, and we will be comparing those hardware performance along with the simulation results, and we will be comparing whether the better performance in the Simulink is the same in the hardware, by applying this control strategy to the same plant. Then for developing the carrier signals, we will be using multi-carrier pulse width modulation strategies, multi-carrier pulse width modulation strategies, that is MCPWM. We will say it as a MCPWM, multi-carrier pulse width modulation strategies. Then in that MLI, I have chosen a better current trending, that is trinary source multi-level inverter. You might be heard about multi-level inverter, in that it is an trinary source, and extra additional beneficiary which this derivative is being obtained, that is trinary source multi-level inverter. Then for voltage boosting, then another supplementary I have taken the circuit is Z source inverter. There are three topologies in the multi-level inverter. You might be taught for your students in the power electronics under the chapter multi-level inverter MLI. There are three topologies, that is cascader multi-level inverter, diode clamped multi-level inverter, flying capacitor multi-level inverter, that is CMLI, DCMLI, FCMLI. You might be heard about and very familiar with this. But regarding these three, I can say on my experience with these topologies, CMLI is been finding better researches among the three topologies, since compared to FCMLI, there is the flying capacitors. This flying capacitors will lead the circuit complexity as well as the cost. Then compared to this diode clamped also, the freewheeling diodes, it's increasing more complexity and more cost, whereas the CSMLI, that is cascader multi-level inverter, that is you can go for cascading of H bridges. You can obtain any number of output levels. So I have been chosen this cascader multi-level inverter. You can also try with this FCMLI and DCMLI also, but there is some disadvantages with that. That is, the thing is cost and the circuit complexity. Then we will be analyzing this validation and analyzes its performance, how this control strategy or the control techniques will be helping us to analyze the performance in primary source multi-level inverter circuits as well as Z source inverter circuits, and we will be concluding our dimensions, our path we have been traveled in the domain of control on applying the control strategy as well as control techniques in the primary source multi-level inverter as well as Z source inverter in performing the outputs, in performing the outputs and giving less total harmonic distortions than without applying the control techniques. It is been giving better total harmonic distortion, that is less total harmonic distortion, better VRMS voltage, root mean square voltage, peak to peak voltage, better VRMS voltage, then as well as less distortion factor in the obtained from the output voltage waveform. So this is our approach. We are going to move in this approach. That is what I have been said is been left hand side you can see the hardware that is being developed beyond this circuitry, that is tiny source multi-level inverter. We have been developed this hardware model with FPGA technique, and below that you can be able to see that a plant for a 9-level, for a 3-phase 9-level trinary source multi-level inverter, where there is 3 bridges for 9-level, that is M-1 for single leg. So for 3 legs, for 3 levels RYB, we have been having the 3 legs and the corresponding switches is being there. Then below you can be able to see the switching states, switching sequence in the plant, and below that bottom is nothing but the hardware implementation, how this Xilinx code is being converted. Then our here that is what our objective is. We have been developing the 3-phase trinary source 9-level inverter. The level we have been chosen is phase is 3-phase, not a single phase. That is 3-phase. Then level is 9-level. Then pulse width modulation strategies. We are going to use the pulse width modulation strategies. Then with the pulse width modulation strategies, we are going to analyze the performance and we are going to predict the results, as well as we are going to develop with this same control techniques in Z source inverter for a 7-level single phase inverter, and for the trinary source inverter we will be developing the hardware model in the FPGA technique. For the selected, we have been choosing 3 references. Among the 3 references, which reference is being better producing the results in simulating? For those, we will be developing the hardware model and we will be comparing it. That is our objective. We are going to see our dimensions in the power electronic circuits. The basics, what everyone knows, this I may not waste much time, just go ahead. That is MLI multi-level inverters. Why we are going for this MLI multi-level inverters means what we are going to decide, to obtain the output AC voltage from the several DC voltages, it can be able to synthesize. There are 3 conventional topologies. That is, one is this diode clamped MLI, flying capacitor MLI, multi-level inverter, and cascader multi-level inverter. The reason going for multi-level inverter is it will synthesize to get a desired AC output voltage from several DC voltage sources. We will be having several H bridges. The input we will be giving as DC source. Instead of DC source, you can go also with the incorporation of renewable energy sources. Also, you can go with solar as well as wind as an input. Instead of giving the DC input voltages, you can give this renewable source. With the help of renewable source, how the performance will be in that same plant, you can also, that is the next level of the extension of this research work. You can also carry out and you can also compare. Then one more thing I want to say, that is I moved with this cascade multi-level inverter. You can also move with this flying capacitor also, and you can also try with this diode clamped multi-level inverters. The research is nothing but once I have been moved in this path, the another person can move in the same approach. You can move with the different topology, and you can see what is the result, what is the comparisons. You can compare and you can predict. That is another research work you can carry out. Then this what we have seen, that is multi-level inverters, the different topologies is cascaded. That is, we are using chosen H-bridge MLI. In the cascaded multi-level inverter, we are going to use cascaded H-bridge multi-level inverter. Then the diode clamp DC MLI, there is neutral clamped. Then in the flying capacitor, that is flying, that is FC MLI, it is that is flying capacitors. Then in the multi-level inverter, you can take this multi-level inverter in different dimensions and you can go with n number of researchers. There are already around 50 to 60 research works are being carried out with this multi-level inverter, and now it is being yet to get saturated. So only there are numerous derivatives that is being arises from this multi-level inverter. For say there is trinary source multi-level inverter, then there is for the same level, instead of giving the same level and analyzing, let us go for symmetrical, that is symmetrical multi-level inverter, or reducing for the same 9 level, we can reduce the number of switches such that we can obtain the same 9 level by reducing the switches. For the 9 level multi-level inverter, how many switches? That is symmetrical, that is the symmetrical. But whereas the also the same voltage, the upper H-bridge if you are giving 15 volt, lower H-bridge you are giving the same 15 volt, but instead of that you are giving the that is the different voltages, upper H-bridge 1 voltage, lower H-bridge another voltage, and you will be reducing the switches such that you can obtain this. You are hybriding the carriers, that is another approach. Then reducing the switches, that is another approach. So you can go for, that is topologies, you can go for topologies, that is any topologies, switched capacitor, reverse connected voltage sources. Then if you are going for subcarrier PWM pulse width modulations, it is carrier based pulse width modulation. You can go for carrier based pulse width modulation also, and you can move with the control techniques of PD, that is phase disposition pulse width modulation technique, POD, phase opposition disposition, alternate phase opposition disposition. This is carrier based PWM. This is what the approach we are going to go. Then instead of that carrier based, you can go for phase shifted also. Phase shifting key, PSK, frequency shift keying. Then ASK, you can go for asymmetrical shift keying also. Then the same control strategy you can apply with the hardware model also, using field pole gate array, that is FPGA, using Spotron 3E, you can go, or for the instead of this DC source, you can use renewable sources also, solar, wind source you can use instead of this DC source, you can use so that is a solar as well as wind source also. You can have a control using, instead of this control strategy, you can have a control using Arduino also. Regarding the performance parameters analyzing, we can analyze percentage THD, percentage total harmonic distortion. We will say THD, that is total harmonic distortion. DF, percentage DF, distortion factor. Then we will say VRMS, that is root mean square, peak to peak voltage. So these are all the things we can analyze for the different modulation indexes. MA, you can vary it from 0.8 to 1, you can vary and you can analyze the performance. That's what the left hand side the top it is being given. THD, RMS value, you can analyze the performance parameters for the same level in the same plant. You can analyze power factor also, and you can be able to analyze the switching loss, that is the power loss. This is the flow analysis. In analyzing the performance, you can take it in different dimensions, the MLI. Next, the modulation, I have been said, the modulation strategies. The modulation strategies, you can go with fundamental frequency switching strategies, or you can go with space vector PWM strategies, or you can go with carrier-based PWM strategies. There are three strategies you can be able to follow with the power electronic circuits. But the space vector means for the entire circuitry switching of 360 degree, you have to plan the coordinates. That has been a little bit difficult. So we have been going with this carrier-based PWM strategies. In that carrier-based PWM strategies, there are two strategies you can follow. You can go with single carrier pulse width modulation strategies, as well as you can go with multi-carrier PWM strategies. That is, you might be seen in the number of papers, MCPWM strategies, or this word you might be come across, MCPWM. That is, what is MCPWM? Multi-carrier pulse width modulation strategies. In this multi-carrier pulse width modulation strategies, you can go with bipolar PWM strategies also. That is, you might have the zero reference. From the zero reference, upper carrier as well as bottom carrier, the lower carrier. From the zero reference, that is top carrier as well as the bottom carrier. Instead of bottom or top, that is bipolar, you can go with unipolar also. This is the n number of aspects or dimensions is there. Dimensions is there which you can choose your that is way of dimensions, and you can go into approach and you can predict the results, and you can say, in my approach, in my dimensions, I have been traveled in this way and I have been predicted this results. So like that, but our approach in this forum is we are going to choose cascaded multi-level inverter. Cascaded multi-level inverter, that is H bridges. The source is DC source. Level is 9 level. Plant is TRINARY source multi-level inverter. Carrier-based PWM strategies. In the carrier-based, we are choosing multi-carrier PWM strategies, and that is regarding polar is bipolar PWM strategies we are going to use. Then we say bipolar multi-carrier PWM strategies. We are being around 7 techniques is there. To be frank, there are 7 techniques, 7 multi-carrier PWM strategies, techniques there is. But I have been chosen only 4 techniques so that it will be a common which can also has to suit for Z source also. So that only I can be able to have a interconnections. What is been happening in the Z source inverter? What is been happening in the TRINARY source multi-level inverter for the same technique, for the same plant? What is been happening? So that I have been chosen the 4 common strategies. PWM, that is phase disposition pulse width modulation, phase opposition disposition pulse width modulation, alternative phase opposition disposition pulse width modulation, carrier overlapping pulse width modulation. Then this is the strategies we have been chosen. Then the references we are going to use is sinusoidal reference wave pattern, trapezoidal reference wave pattern, then tri-reference wave pattern, that is called third order harmonic injection. Third order harmonic injection. This is the set of references we are going to use it in our circuitry. Then carriers we are going to use is fixed amplitude triangular carrier, that is called FATC wave pattern. Fixed amplitude. The carrier will be the amplitude of the triangular carrier will be, the carrier is triangular carrier. The amplitude of the carrier is fixed. For example, the height of the carrier is 0.8 means as well as for bottom carrier. Instead of this fixed amplitude, you can go for variable amplitude also. The first carrier, it may have some 0.8 height, 0.8 amplitude height, and the second carrier, it may have some 0.6, third carrier some 0.4. Like that, you can go for variable amplitude triangular carrier, that is VATC wave pattern. The next one is rectified sine carrier, that is RSC wave pattern. So you have been chosen the carriers for the plant chosen. What are the carrier we are going to use? What are the references we are going to use? For these references and carriers to the plant, what control strategies we are going to use. So our control strategies, that is PD-PWM, POD-PWM, APOD-PWM, COPWM, that is carrier-based control strategies. These control strategies, how it is being developed, and how this control strategy is going to involve in generating the carrier signals, which helps in producing the output voltages with less THD, less total harmonic distortion, less distortion factor, and peak VRMS voltage, that is peak voltages. In the output voltage, our expectation, the output voltage should be a peak output voltage. The distortion should be less. Distortion factor should be less. This is what we expect from the power electronic circuitry, so that we are going to use these output voltages that is being obtained from the trinary source multi-level inverter to a high voltage application as well as for medium voltage applications. Next. We are going to see how these carriers is being developed. MATLAB simulating only, but I may not be able to show this originally now as on time how it is being stimulated, but whereas in the requires some 2 to 2.5 hours time the simulation will take. Then also my laptop also, it is better higher versions which is not that is supporting my earlier simulation work. So I have to see to that. So in that time respect, I will take you to the dimension what the power dimensions towards the power electronic circuits. All these stimulated waveforms is been obtained originally. This was the reference and carrier arrangements for a fixed amplitude triangular carrier. The first one left hand side you can see, that is the carrier arrangement for PWM. This was the carrier is fixed amplitude triangular carrier. Fixed amplitude triangular carrier. Reference we have been chosen is sinusoidal reference we have been chosen. Carrier amplitude is fixed amplitude. You can be able to see the middle is the zero reference middle. You are having four carriers. Upper you are having 4 carriers, bottom you are having 4 carriers. The carriers will be having the same amplitude. But whereas in case of a variable amplitude, the height of the carrier, it may be different. Will be generated means in this PD-PWM, the carriers will be of same frequency. You can be able to notice same frequency, and as well as the amplitude also same peak to peak amplitude. So suppose one amplitude means all the 4 carriers in the top as well as in the bottom, the height is peak to peak amplitude is same peak to peak amplitude, and frequency is same. They are being disposed, their bands and occupy which are being contiguous. The modulating wave of the fundamental frequency are placed at a zero reference. From the zero reference it is started on all the 4 carriers in the bottom as well as in the down below the zero reference. All carriers is been having same equal amplitude of 1 volt. The frequency is same frequency. Then here the carrier is being placed above as well as the below the sinusoidal carrier. Since it is a three phase, you'll be having RYB three references, and these three references is being placed above the zero reference as well as below the zero reference. The reference is greater than the carrier signal, then the active devices corresponding to the carrier is being switched on, whereas the other devices will be switched off, Then this carriers is being developed for modulation indexes. The sample I have been taken and put, this sample is being developed for modulation index equal to 0.9 as well as modulating frequency is 40 Hz. For 40 Hz only, all these four carrier arrangement is being developed and modulation index is for 0.9 it has been developed. Then coming to POD, here the first one for PWM, the sample is being put is sinusoidal reference, whereas here it is trapezoidal reference. Then the strategy is POD PWM, that is phase opposition disposition PWM. The phase opposition disposition PWM, how the carriers is being developed means the carrier waveform above the zero reference or in phase as well as in below zero reference or being is shifted at 120 degree. Above the zero reference you can see the carrier waveform, and below zero reference it is being shifted at an angle of 180 degree. That is the difference compared to PD-PWM strategy as well as APOD PWM strategies. The carriers are being in the upper as well as lower or in phase. The phase is being shifted at 180 degree. But the modulation strategy, the carrier arrangement obtained is for same modulation index of 0.9 as well as for modulating frequency of 40 Hz. Then coming to the third one, that is APOD PWM, that is alternative phase opposition disposition PWM. Here the references is tie reference, third harmonic injection reference. The amplitude is here it is being used. The amplitude, how it is being used means each carrier is out of phase by 180 degree, whereas the POD PWM is in phase with 180 degree, whereas the APOD PWM is 180 degree out of phase, and here it is used variable amplitude. Then it is being developed for same modulation index equal to 0.9 as well as modulating frequency equal to 40 Hz. Then coming to this carrier overlapping, COPWM means carrier overlapping pulse width modulation strategies, in which the carrier is developed. That is, here the carriers will be having same frequency, same peak to peak amplitude, which will be disposed and they have overlap with each other. The overlapping carrier is AC by 2. That is the overlapping angle divided by 2. It is being followed, and here different modulation index will be followed. That will be taken as modulation index MA equal to AM by 2.5 into AC. That is 2.5 is nothing but this what the carrier is being developed for the four strategies. The first one is PD, phase disposition pulse width modulation strategy, phase opposition disposition PWM strategy, and this is APOD PWM strategy, alternative phase opposition disposition PWM strategy, carrier overlapping PWM strategies, and the reference is sinusoidal reference, here trapezoidal reference, and here third harmonic injection reference is being followed. And then this is chosen reference and carrier arrangements for rectified. The previous one is for fixed, that is for variable amplitude carrier you have been chosen. Then this is for rectified sine carrier, You can be able to see the carrier arrangement, the shape. It is rectified sine carrier. The control strategy, either it may be PD, APOD, that is POD, APOD and CAPWM. It is the same strategy only. But here the reference and the carrier arrangement is done for rectified sine carrier. The next, this is the plant, the left hand side, you have been chosen this plant. This is the plant for three phase. Phase is three phase. You are having three legs, RYB, which is being neutral clamped. The load we are using is static load. This circuitry is static. Under static, we are using R load, RL load. You can use RLC also, but we have used RL load. RL load we have been used. Then this is for it's been obtained in case of open loop, but we have been using this control strategy, PD, POD, APOD. The same also we can implement in closed loop system also. This closed loop system, you can be able to apply the control for a dynamic machinery, dynamic load. Suppose the same power electronic circuit is being used as a load connected to induction motor or to any dynamic load. If you are connecting, there you can use it the closed loop system, and you can analyze their control functions. But we are here, it is static one. So we are using the load is RL load, and we are applying the control strategy PD, POD, APOD and the COPWM. Then it is a 9 level. You are having 2 bridges for each leg. Then why I have said is as trinary source multi-level inverter means the VDC is in the ratio of 1:3. You can see here that is left hand side 1 VDC. Then the lower H bridge I have been taken is HB2 is 3 VDC. So the VDC is 3. There is 3 VDC. Then the simulation parameters I have used is VDC is 100 volt. For single VDC it is 100 volt. 3 VDC means you have to use 300 volt. Then load, our load I have used is 100 ohm. The carrier frequency is 2000 Hz. I used modulating frequency is 50 Hz. These are the two switching states that is being obtained for a single phase. It is being given the output switching states have been shown how the 9 levels 0 plus VDC, 2 VDC, 3 VDC, 4 VDC. It is being obtained in the higher, that is the above 0 reference, and below 0 reference 0 minus VDC, minus 2 VDC, minus 3 VDC, minus 4 VDC. It is being obtained the bottom side. This is the switching states. How the active port will be the corresponding, those switches will be in active, other switches will be in off conditions. Then this was the performance. We have been developed that simulations, and we are analyzed by varying the modulation indexes from 0.8 to 1. We are varied the modulation indexes starting from 0.8, 0.85, 0.9, 0.95. All the reference, that is carrier arrangement, is shown for 0.8. The sample is taken for 0.9 for all the references, and it has been shown there. The parameters we have taken is percentage THD, percentage total harmonic distortion, percentage distortion factor, and the maximum peak to peak voltage. The control strategy we have used is the 4 control strategy, and we are used the references for sine what happens, for trapezoidal, and for third harmonic injection reference. We have taken this as a common control strategy. The same plant reference is being different, how it is been working. If you see, they have been highlighted. If you take the total harmonic distortion, it is been better in PD, PWM, that is phase dispersion. It is been better, which is been producing compared to other 3 techniques, compared to 3 references. This PD, PWM is been better with in trapezoidal references. When you use trapezoidal reference, the harmonic is being least in PWM. Compared to distortion factor for sinusoidal reference, in APOD it is being least. Better is voltages better, the peak to peak voltage is better in case of carrier overlapping when you use third harmonic injection references. This is the performance analysis. This is a graphical representation for those analyses. You can be able to obtain the percentage THD versus modulation indexes, the performance analysis, graphical representations, and here the percentage distortion factor versus modulation indexes. You can be able to have graphical analysis. Then the conclusion from this is what is the harmonic content of the output voltage is least for PWM strategy with the trapezoidal reference. Carrier overlapping strategy with tie reference provides the highest DC bus utilization. On the other hand, all the other strategies have comparatively the same DC bus utilization, which is lower than COPWM strategy. Distortion factor is less in POPWM strategy with the sign reference. This is the conclusion we have been obtained using this control strategy. Then that is for that is the fixed reference. This is for variable amplitude. If you go for this variable amplitude carrier, the percentage THD is less in trapezoidal reference in POD PWM technique, and distortion factor is least for tie references in PD PWM technique, and VRMS is better in COPWM technique. Then if you the same graphical representation in the similar manner, then from here what you comparing is the harmonic content of the output voltage is least for variable amplitude, that is POD PWM, harmonic content is least for with trapezoidal references. Carrier overlapping, it is with tie references providing highest DC bus utilization compared to other DC bus utilization, which has been lower than COPWM only. Distortion factor is less with variable amplitude pulse width modulation strategy with tie references. Then with the rectified sine carrier, we have been made the comparison the similar manner. Here also in the trapezoidal reference, only in PD PWM it is least, and in sine reference it is been distortion factor is least for PD PWM, and for VRMS it is in tie references only, it is been better. The similar manner graphical representation we have been obtained, and we are concluding it is least in harmonic content is least in PD PWM with a trapezoidal reference, and COPWM strategy with a THA reference providing highest DC bus utilization compared to other techniques, and DFE is least with the PD PWM technique. Then this what the comparisons related to trinary source multi-level inverter. With the trinary source multi-level inverter, the output voltage is better with a carrier overlapping strategy. If you want to obtain better output voltage, means you have to use tie reference, that is third harmonic injection reference with a carrier overlapping control strategy. Then if you want to have least that is distortion factor, means you have to use PD PWM technique for with the reference you have to take is trapezoidal reference. Then if you want to have least distortion factor, means you have to use PD PWM strategy for tie reference. So what you have to choose is depending upon your application necessity. If you are going for high power applications or you go for low power applications, to that your application which is being required better, whether you want to have better output voltages or you want to have less total harmonic distortion or you want to have less distortion factor, that you have to choose depending upon your application, whether you are going for low power application, high power application, where you are going to apply in which domain. So it's your duty to choose. Then this another approaches with a Z source inverter. Why it is being called as a Z source inverter? The source in the previous circuitry and all, it is been the DC source, but here one thing it is been different. What is the different means? The source, it is from the source side. from the source side, the component of L and C, it is arranged in the shape of a Z. Shape of a Z. So only it is called as Z source. So only it is called as Z source. From the source side, the L and C is arranged in the form of in the shape of a Z, which is being used to boost the voltages as well as buck the voltages. That is being the components is being arranged in the source side. So it is called Z source fed. The level you are using is 7-level cascaded multi-level inverter. This is being developed for single phase. We can develop it for 3-phase, nothing wrong. But when you go for this hardware implementation and all, so many L and C components, that is inductance, capacitance, that is switching, that is all it's getting bursting. So that only we tried with the initial stage, we tried with this in single phase. But later on, my colleague in Milam Engineering College, also Dr. Prem Kumar, he tried with 3-phase and he has successfully obtained the outputs also in better way. He tried later on beyond me. Then there are many derivatives depending upon the arrangement of the source. That is L and C at the source side. It is embedded, that is embedded C. You are going to embed the inductance and capacitance at the source side. It is called embedded C. Then quasi Z source. It is been depending upon, there are 2 derivatives. Then also T-shaped. There are so many derivatives that is being come along with this Z source inverter. This is what you can be able to see clearly. The first one is sinusoidal. For PD PWM strategy as well as for PD PWM strategy, 2 reference you have chosen, sinusoidal reference, trapezoidal reference. The arrangement, it is being in phase. The next, you have been obtained the results for Z source multi-level inverter, for embedded Z source multi-level inverter, and for quasi Z source inverter with all these 4 strategies and with for these 3 parameters, and you have been analyzed with a sine as well as trapezoidal for single phase for 7-level, and we have been proved the control strategy. For trapezoidal, the total harmonic distortion is less and distortion factor is in quasi Z source CMLI, it is less with the sine reference, and the VRMS voltage is better with the trapezoidal reference in quasi Z source multi-level inverter. The similar manner, the graphical representation and the observation, what in the tabulations we said is I have been given here, and this is the hardware implementation. What is being better in the simulations for trinary source, we have been developed in this hardware. That is, I said, there is FPGA technique. This FPGA technique with Spotron 3E, we have been developed. The simulations will be directly converted into, that is, Xilinx codes using this Spotron 3E. That was we can be able to see in that picture, the photo shots. You can be able to see here in the hardware model. We cannot go with the implementation with the same range of the simulation results. You have to reduce in the order of 1:3 or 1:5 depending upon your that is components available, the voltage ratings and also. You have to that is cut short the ratings in the ratio manner. That is, I have been here chosen, that is VDC is 5 volt, R load is 100 ohm, and carrier frequency is 200 Hz, the modulating frequency is 50 Hz. Then for fixed amplitude, variable amplitude, and for rectified sine carrier, for references, that is for trapezoidal, we have developed this hardware model and we have been obtained this results. It shows for percentage THD, it is for variable amplitude carrier only, it is least in case of PD PWM. Then distortion factor is least in case of in fixed amplitude with PD PWM. And for VRMS, it is better with variable amplitude only, the voltage is being better. the graphical representation for hardware results, and this what I have been said in the tabulation what you predicted. From this summary, the entire the simulations as well as the hardware, what is the summary we are going to conclude is our way of dimensions control strategy. We followed phase with the PD technique, phase dispersion pulse width modulation technique, as well as POD, APOD, COPWM. We have followed in this tiny source multi-level inverter as well as the Z source multi-level inverter, and we have obtained the results. From this, we have to choose for which applications this circuitry. This circuitry can be applied in electrical utilities as well as in renewable energy systems also. Where if you are going to use in renewable energy systems, which parameter, whether you are going to use in medium voltage, high voltage, which you want the peak to peak voltage is to be better means, according to that you have to use COPWM technique. If you want less THD means you have to reduce the total harmonic distortion, where you are going to apply it in medium voltage application means you have to use PWM technique. This is what the dimensions we have traveled and we have been understood from the simulated results as well as for hardware results obtained. This is our dimensions we moved with the power electronic circuits. The plant we have taken is 3-phase 9-level trinary source multi-level. In this similar manner, you can go travel in different paths and you can have your own dimensions and you can obtain your predicted results. This is what I want to say. Okay. Thank you. Any more questions, queries? Thank you. Thanks to everyone.
Dear participants, now you can post your queries in the chat box. Sir, there is a question, sir.
Sir, I will read it, sir. No problem. Thank you. That is Aishwarya Saktivel has been asked, why resonant converters are not used frequently and not much research carried out on resonant converters, though it reduces switching losses, EMI, etc. That is a very good question. The switching losses, the switching losses, by calculating the switching losses compared to distortion factor as well as crust factor or percentage THD, or calculating the root mean, that is VRMS voltage in the simulating, it is been very easy. But the switching losses, calculating switching losses means it involves the equation, that is in the equations you have to calculate the, you have to adopt the formulas and you have to go with that different approaches. So in that simulation itself, it has been little bit difficult in calculating the switching losses as well as the EMI. So only they are not using the resonant converters. Instead of this resonant converters, they have been moving with these derivatives of MLI. Derivatives, why means this MLI will having the lot of applications where it is being used in the current trending for medium voltage applications as well as for high power application. Instead of this DC source, you can go and put the renewable energy sources and you can obtain your better output voltages for your renewable applications. So only all these resonant converters and all, it is being outletted and they are going for these derivatives, and circuit complexity also you can reduce in the case of these multi-level inverters. You can go for even symmetrical, asymmetrical, you can go for hybriding also the carrier arrangements. So lot varieties and complications. We can say my well-wisher Dr. S.P. Nadarajan, professor and head retired from Annamalai University in the Department of Instrumentation Engineer, he used to say one word, it is MLI, it is control free degree. Control free degree. That is, you can take it to any 360 degree. Like eco-friendly, it is, you can take it to any 360 degree. That's what the current trending is being with even more and more researches is being carried out with the MLI. Even it is being now, it is trending with the derivatives like that is reducing switch count, going with the derivatives of MLI like TSMLI, trinary source multi-level inverter, and the Z source inverter, then embedded Z source, quasi Z source, T clamped, like that. There are numerous derivatives. It has been going on along with this MLI, which is been performing better far and far compared to the resonant converters. Even though it has been reducing the switching losses and the electromagnetic interference. The next, that is, I welcome Professor Rajaguru. He has been the colleague in Kongunadu Engineering College. Earlier, I have been seen, meted. Thank you, welcome, Professor. You have been put up your question. What are the recent controllers for the power system? Recent controllers.
Good evening, Professor. This is Rajaguru.
Yeah, Professor. Yeah, good question. Thank you.
Once again.
Okay, thank you. That is, what are the recent controllers for power system application with respect to research point of view? That is, my friend, colleague, Dr. S. Ramesh, he has been done the research better 10 years before. When I am not doing the BME itself, he has done in artificial intelligence, neural network, with that is the control techniques. He has been done the research work. He used to say, even from before, that is 10 to 15 years, he has completed the research. Though in those days, he completed the research with artificial intelligence, AI, GA. Then now he traveled along with so many techniques, that is beef algorithm, then that is honeybee, the beef, that is DATS, butterfly algorithm, particle swarm optimization. All these techniques, the recent technique is come into existence also. But he used to say GA is being far better than this new trending techniques that come into arises day by day. And he also proved in 2 to 3 seminars and workshops how this GA is been performing better. But then I can be able to give, he has been very well versed in these optimization techniques. If you want to do any trending researches with this optimization techniques, I can give his email ID as well as a mobile number, and I can also refer you closer, and he can be able to sort out your answers in a better way. But as far
Thank you so much, sir.
Thank you, Professor. I learned from him for the past 10 years, and he also proved me in many of the forums. He used to say GA has been a very good optimization tool regarding the power systems applications. The next, thank you, Professor. The next, Kirba post all questions. Then Karnagaran Professor has been pointed out the question, how the optimal control and adaptive control techniques are used in power electronic converter. This optimal control and adaptive control, I have not used it, Professor, but in forthcoming days, I will use it and say how it is been behaving in power electronic circuits. Either this optimal control as well as the adaptive controller. I have not used it so far. I will use it and tell in the next 2 forums wherever I give. Then very nice presentation. Thank you, Professor. Then another is Subramanian sir has the difference between PAM, PWM and PPM in. Okay, that is Professor. The PD, that is phase dispersion. In that phase dispersion, we will be setting the carriers with the same peak-to-peak amplitude. Say peak-to-peak amplitude with the same carriers. The bands will, from the zero reference, it is been occupying the same height. That is above the zero reference as well as below the zero reference. It is been occupying the same height. And it's also occupying the same distance. That's what we used to say the word called contiguous. It will occupy the same distance. But whereas, if you compare, I can be able to go to that slide and say, the first one, it is been, if you see from zero, there is zero reference at the top as well as the bottom also, it is been contiguous. the same equal amplitude, it is been having, that is occupying this space as contiguous, same peak to peak amplitude and same frequency, the carrier is set up. When the modulating wave of the fundamental frequency is placed at the zero reference, the carrier will be placed above as well as below the zero reference, and if the reference is greater than the carrier signal, then only the active devices corresponding to that particular carrier will be switched on. Otherwise, the devices will be switched off. That is the case of the PWM. But whereas when you come to the phase opposition disposition pulse width modulation technique, the same carrier waveforms above the zero reference will be in phase, and but the angle will be 180 degree. That's what the difference between PWM as well as APOD PWM regarding the carrier arrangements. Coming to alternative phase opposition disposition, from the zero reference, the carrier will be out of phase with the neighbor by 180 degree, whereas the PD, it is same height, same equidistance, so we are calling it as contiguous, but whereas POD will be in phase with 180 degree above zero reference or below zero reference, and whereas APOD PWM, it is out of phase with 180 degree, the carrier arrangements. Then comparing to COPWM carrier overlapping, the overlapping angle will be 1.6. Regarding this circuitry, there is a formula to calculate the overlapping angle, which will say that is AC by 2, the carrier modulating carrier divided by 2. That is, for each carrier we have to calculate AC by 2, and modulation indexes also, it is a different formula, MA equal to AM divided by 2.5 AC by 2, and modulation indexes also, it is a different formula, MA equal to AM divided by 2.5 into AC. This is what the differences regarding each carrier. Then Ramesh Babu sir has put up a question: while implementing the hardware setup, how can we fix the deadband angle between the switching pulses for variable R load? Regarding the hardware setup, how can we fix the deadband angle between the switching losses? Professor, I have not calculated the switching switching losses and all, professor. Here I have been calculated only these four parameters only. The switching losses, it goes the another researches. So only I have not carried out only these four parameters: percentage THD, percentage distortion factor, and the test factor. I have been calculated, but I have not put up in this presentation. VRMS. This switching losses I have not carried out. Then what are the types of DC waveform? Different types of DC waveform. The waveform I have been put up with this. There are numerous waveform, but we carried out only for these three. That is fixed amplitude triangular carrier and variable amplitude triangular carrier, third harmonic. There are many carriers. What we have been followed in the Rashid and Bimbra only. I have been developed beyond that. The suggestions given by well-wisher Dr. S.P. Narrajan only, I have been to come forth. Then, okay sir, thank you. Not losses, sir. Switching pulses. Switching pulses in the sense, modulating switching pulses, what you have been asking. Can you unmute Ramesh Babu sir? While implementing the order. Yeah. You have been put up. That is while implementing the hardware setup, how can we fix the dead band angle between the switching pulses for? Sir, this there is no need to worry about this dead band angle and all. But what I have done is this the entire simulation model. What you developed. If you give it in Xilinx means using these Xilinx, they are converting into as a using FPGA, the Spotron 3 is converting directly into Xilinx codes. From the Xilinx codes, you can be able to obtain the waveforms and all, and readings also you can be able to obtain this. They have been doing with this Spotron 3, they have been doing in numerous places. They have been doing. You can go with VA Microsystems. VA Microsystems, they have been having this better spectrum analyzer. With the better spectrum analyzer, there is three-phase spectrum analyzer and all. They are having. You can be able to, if you give that simulation link means they will be easily converted into Xilinx codes. From the Xilinx codes, you can be able to obtain this and all. There is no need to go for this worry about this dead band angle fixing and all. Okay. Thank you. Any help, participants? If you want any help regarding the research work and all, any suggestions if you required, I have been put up my mail ID and mobile number in the different present in itself. You can make a note and you can put a mail. Most probably after 5, that is 6 p.m. you can call it, or you can put a mail. Whenever I be free, I can be able to give suggestions. I can be able to lead it in dimensions what you require. I can be able to help you. Then,
sir, shall we end with the session, sir?
Yeah, sir.
Okay, sir.
Okay, Professor. Now I request our Professor Mrs. Kirba to deliver the vote of thanks. Madam.
Good evening, all. As all good things come to an end in life, so is the workshop. On behalf of SRM TRP Engineering College, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this workshop on dimensions of control system organized by our institute. First of all, I extend my most sincere thanks to Almighty God for making today's event a resounding success. At the outset, I thank our chief guest, Dr.T.Sengolrajan, Associate Professor, Department of TRINARY, Kongunadu College of Engineering and Technology, who spared time from his busiest schedule to grace the occasion. Today, we had an opportunity to hear your thoughts on applications of controllers in power electronic circuits. We are really enlightened with your knowledge. Thank you, sir.
Thank you, ma'am. Thanks to the organizing committee as well as I wholeheartedly thank the HOD Tribly, Dr. Elangovan sir and Tony Raji sir, then my colleague Rajaguru sir, then I thank the management overall SRM TRP for inviting me and to share my knowledge on the power electronic circuits control strategies in this forum. Thank you all. Thank you, sir.
Thank you,
sir.
Sir, thank you very much for spending your valuable time, sir.
Thank you, sir. This is Rajaguru, sir. Very nice presentation, sir.
Thank you, sir. Sir, you can call it or you can mail whatever you are.
I will contact you, sir.
We are free to help you, sir.
Okay, sir. Okay, sir.
Okay.
Thank you, sir. Thank you, sir.
Thank you. Okay.
Thank you, sir. I would like to thank our principal, Dr. B. Ganesh Babu, sir, for being the catalyst that stimulated us to do our best and standing us pillars of strength. Thank you, sir. I would like to thank our Vice Principal, Dr. B. Ramasubramanian, sir, for his motivation and enthusiastic support. Thank you, sir. I would like to thank our HOD, Dr. P. Ilangovan, sir, for guiding and providing his continuous support. Thank you, sir. A special thanks to the organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Thank you all. Finally, our heartfelt thanks to all our participants for their active participation and made this workshop a grand success. With these warm words, we move to the end of today's workshop. Thank you all.
Sir, Tony Raj, sir. Shall I leave, sir?
Yes, sir. Thank you very much, sir. Thank you very much, sir.
Sir, tell me, sir.
Thank you very much for your valuable time, sir. Really, it's a wonderful session, and most of our participants have enlightened with a great knowledge, sir. Thank you very much, sir. Thank you, sir. Thank you, sir.
Thank you, sir. Also, we will help them, sir. We will get path. We will guide them in the.
Sure, sir. Sure, sir. Thank you. Thank you very much. Thank you very much.
Okay, sir. Thank you. Thank you.
Participants, you can fill the feedback form and you can take a leave. All your certificates will reach you within coming Wednesday, that is 13/1/2021. Okay, it will reach within 13/1/2021. We'll generate the certificate and let you know. Kindly, you fill the feedback form. The feedback form will be open till 9 o'clock. Kindly make use of it and fill the feedback form as soon as possible. Thank you very much. All of you can take a leave. Thank you.
Thank you, Tony, sir. Kirpa, ma'am. Kritika, ma'am. Thank you very much, sir.
Thank you, sir. Thank you, Professor. Thank you, Professor.